In this example, we're told that we have two colleagues who are tasked with measuring the mass of 5 nearly identical pennies, so like what we have in the picture here, using a mass balance. So one of the colleagues recommends measuring the mass of each of the 5 pennies, so measure each penny separately and obtain an average value from the 5 measurements. And then the other colleague says, take all 5 pennies and weigh them simultaneously. So stack them up, weigh them simultaneously, and then divide by 5. So which measurement is the one that'll have the least uncertainty? Another way to say this is which measurement's really the best way to do it so that you have the smallest uncertainty, since having a small uncertainty obviously is desirable. And we need to support our answer. So what we'll do is first consider the case where we measure each penny mass separately. So imagine we have our balance and we put each penny on it. So when we make our measurement, we'll get the measurement for the first penny. We'll just call it M1, and it'll have some uncertainty. We'll call it delta M. Now delta M is the uncertainty that we get from our mass balance. So let's say the mass balance has a least count of 1 gram. Then our uncertainty would be plus or minus 1/2 of a gram, right? So we do that 5 different times. And the uncertainty in each measurement will be the same because we're using the same balance, right? So each time, if our least count was 1 gram, then our uncertainty would be plus or minus 1/2 a gram, because we're always using the same scale. And then of course our average mass for the penny would be 1/5, and then you add up each of the measurements. Right? So that would be our average penny mass. Now, that's giving us our average, but now let's calculate the uncertainty associated with that average measurement. So we're trying to get the absolute uncertainty in the average. That will be following our propagation of uncertainty approach. That'll be the absolute uncertainty in the average measurement due to the absolute uncertainty in mass 1 squared, plus we do that for each measurement. So we're just getting the absolute uncertainty in the average due to the absolute uncertainty in each of the measurements. Okay. There we are, and then we sum those all together and take the square root of it. So that comes from our propagation of uncertainty approach. Now each one of these will have the following absolute uncertainty. So to find the absolute uncertainty in the average due to the uncertainty in mass M1, what we do is we'll take the derivative of the mean divided by M1 times the absolute uncertainty in M1. So when we do this derivative, the mean would go back up into here, and you'll see it's just equal to 1/5, or 1/5 times the absolute uncertainty. The absolute uncertainty in M1 is just this delta M. And that'll be the same for each one of these, right? Because if I did this same calculation sub M2, then I'd have dm bar divided by dm2. It's still also going to be 1/5. And then the absolute uncertainty in the second mass measurement will still be delta M. So they'll all look exactly the same. So when I substitute this in, I'll have 5 of these measurements, because all 5 of these look exactly the same, so there'll be 5 of them, and then this will be squared, so they'll all look like that, and so this will be the square root of 1/5 delta M squared. So the absolute uncertainty in the average mass will be 1 over the square root of 5 times the absolute uncertainty in any one of the measurements. So that's the uncertainty we would get in our average mass measurement. Okay, so it'll depend on the least count of the scale that we used. Divide that by 1 over the square root of 5. And here's our mean value, so it'll be our mean value plus or minus this delta M, right? We just jot that down here. Right, so that's how we would report our measurement, I should say. So that's method 1, where we make each measurement individually. Now let's do method 2. So for method 2, what we're going to do is put all 5, so let me draw a little sketch here. Here's our scale, and we're going to just put all 5 pennies on there. We're going to put all 5 pennies on there and make a single measurement. So that single measurement we'll just say is equal to, we'll just call it M, capital M. So that's our single mass measurement, and of course that will have some uncertainty, and that uncertainty will still be the same as the uncertainties up here because we're using the same scale which has the same least count. So recall that when I was talking about this part of the problem, I said the least count was 1 gram, so the uncertainty would be plus or minus 1/2 of a gram. So that uncertainty here would still be plus or minus 1/2 of a gram. And M here is really our 5 measurements. So to get the mean value, we'll just take 1/5 of that single measurement, right? This is a capital M. Maybe I'll do it that way. So that's how we would get our mean value. So now let me calculate the uncertainty associated with that. So the uncertainty, absolute uncertainty in the mean value would be square root of the uncertainty in the mean value due to the uncertainty in our capital M measurement squared. That's it, because we only have the one measurement. If we do our propagation of uncertainty calculation, our uncertainty in the mean due to the uncertainty in capital M will just be the derivative dm bar over d capital M times the uncertainty in capital M. This will just be 1/5, and this will be dm, the little m. So the absolute uncertainty in the capital M measurement is just the uncertainty that we get from the scale. It's right up here. And then this derivative just comes from right here. So we can substitute that in, and you see that our absolute uncertainty in our mean value here will just be 1/5 delta M. So that's the, and of course our mean value would be, just the mean value plus or minus delta M bar, just as we had before up here. Okay, but our uncertainty here, our absolute uncertainty here is 1/5 delta M. Here it was 1 over the square root of 5. So this one actually has a smaller uncertainty to it, right? This has a bigger uncertainty, and this one has a smaller uncertainty. So we're better off using this second method where we stack all the pennies together, make our mass measurement, divide it by 5, because our uncertainty there is actually going to be smaller than our uncertainty up here if we measure each one individually. And the reason for that is because down here we just have one measurement. We have one uncertainty that we have to deal with, whereas here we have 5 different uncertainties. And remember, the uncertainties, they add together here like this. It's not a true, just plain old linear sum, but the uncertainties combine together. That's probably a better way to say it. They combine together so that your overall uncertainty is actually bigger than if you just had the single measurement. So anyway, the answer here is, which measurement will have the least uncertainty? The second measurement method will have the least uncertainty, and we supported it by using our propagation of uncertainty approach to actually prove it. This technique of where you combine measurements and then, like what we did here in method 2, that's called stacking, and it can sometimes be used to help reduce the amount of measurement uncertainty you have. Okay, we'll go ahead and end our example there.